The title of his talk is Flexural tensegrity. This is a joint work by Claudio Boni, Marco Silvestri, and myself, Gianni Royer-Carfagni, all of us from the University of Parma. The term tensegrity was coined by Buckminster Fuller to indicate a structure whose integrity is granted by tensile members, usually cables, which are pretensioned by matching a few compression struts. Flexural tensegrity represents a concept that is somehow complementary, since we consider the integrity under flexure of a chain of elements in unilateral contact, which is given by tension and tendons. A schematic representation is illustrated in the figure. The constitutive segments supposed to be rigid are piers to host a shaft through which an elastic cable can slide with negligible friction. When forces are applied to this structure, to this segmental beam, this provokes the bending because the tendons keep the segments together. A fundamental point is that the contact surface of adjacent segments are appropriately shaped so that they are driven to relatively move one with respect to the other in a defined way. The kinematics is completely described as pure rolling contact with no sliding along the design pitch lines. As can be seen in this picture, the effect of a relative rotation of adjacent segments is that of elongating the cable of a quantity lambda I at each cross section. This, of course, affects the elastic energy stored in the cable. The internal bending moment at the ith cross section reads Mi is equal to Ai multiplied by N, where the level arm Ai represents the distance between the pitch point and the line of a tensile force N in the cable. We use a variational approach. We observe that the only contribution to the elastic energy is that associated with the elongation of a cable. Then we use as variable the angle phi of each segment that composes the segmental beam. We have to enforce a constraint that as a function of the angle phi, the total length of the beam remains the same in the deformation. Thus, we use the Lagrange multiplier technique, and using from the first variation of the total energy, we obtain this equilibrium equation at each cross section, which correspond to rotational equilibrium, this constraint, and in all these equations we have a few quantities. First of all, the parameter N, which represents the tensile force in the tendon, which is the sum of initial pre-stress and 0, and delta N, which is the variation of the tensile force due to the elongation of the cable. Then we have that the constitutive equation, which corresponds to the specific law that correlates the level arm, the internal level arm AI, with the relative rotation delta phi of any two consecutive segments. Then we have lambda, which corresponds to the sum of the sectional elongation lambda I, and we have the Lagrange multiplier mu here, and this Lagrange multiplier is physically represented by the constraint reaction. From the point of view of manufacturing, in order to achieve the desired rolling motion along the pitch lines, we find it convenient to use a double couple of conjugate profiles, which are profiles that remain in contact with one another during the motion. This picture represents a schematic view of the joint between any two segments. All red profile, this one, and this one, belong to one segment, while the blue profile corresponds to the adjacent one. As the segments are relatively rotated one with respect to the other, the conjugate profile roll and slide, and there is only one configuration for which the two profiles of each couple are contemporaneously in contact. This configuration corresponds to that achieved by the pure rolling along the pitch lines. Construction of each couple or conjugate profile is made with the method of the normal, the so-called method of the normals, by observing that the normal line to the contact point passes at each time through the corresponding pitch point of the primitive pitch lines. The profiles are incorporated in each segment, which is composed of 3 layers. The 2 external ones, this one and this other one, correspond to the 2 couples of conjugate profiles, whereas the central layer, which is this one and this one, of course, reproduces the pitch line. Indeed, this central layer is redundant because the motion is completely defined by the conjugate profiles only, but it is added because it hosts the cable shaft and drives the deformation of the cable. The manufacturing can be conveniently carried out with a 3D printer through the deposition method, because each layer rests on the previous one. This picture shows the configuration consequent to a relative rotation of the segments. One can see one portion of the cable, this one, which remains exposed. This is the one represented in red here. And of course, this corresponds to the sectional elongation of a cable. We have manufactured prototypes of total length 621 millimeter, which have been made with a 3D printer using PLA. The cable is a polyamide 6.6. It is a wire with diameter 1.1 millimeter. An additional spring has been added at the beam ends, and the composition of the stiffness of the wire plus the additional springs provides an overall stiffness of 1.1 Newton per millimeter. The weight of each segment is variable from 2.3 to 0.9 Newton according to the specific model that has been constructed. Here you can see the 3D printing of a segment. This is the end spring that is added, and here it is the deformation of a prototype under its own weight. The constitutive laws that define all the stiffness of the segmental beam are completely described by the relationship between the internal level arm AI and the relative rotation delta phi I of the consecutive segments. Recall that AI is the internal level arm and delta phi I is the relative rotation, and since the adjacent segments are supposed to remain in contact along the pitch lines, AI is just a function of delta phi I. And we have considered three cases in which this relationship is either linear, as represented in green, or sublinear, as represented in blue, or superlinear, as represented in red. Remarkably, the AI as a function of delta phi I is the first derivative of a function lambda I as a function of delta phi I. For example, in order to obtain a linear AI as a function of delta phi I, we should have a quadratic lambda I as a function of delta phi I. Recall that lambda I is the elongation, the sectional elongation of the cable. So we have constructed these three different prototypes, and here we have a schematic view of the corresponding 3D printed segments, which are the constituent, the basic constituents. And as you can notice, the only difference is represented by the shape of these profiles. This video shows the deformation of one of the segmental beams for the sublinear case. This other video shows the response of a much longer structure. As you can see, there are some similarities with the loops in a classical Euler elastica. For each type of constitutive laws, that is linear, sublinear, and superlinear, we have considered the three types of pre-stressing forces in the cable. This is linear, and these are the pre-stressing force. This is sublinear for the corresponding three pre-stressing force, and superlinear with the corresponding three pre-stressing force. Of course, these are just the initial pre-stress, and then the stress, the tensile force in the cable may vary because of its elongation consequent to the deformation of the beam. We have made experiments by considering end forces equal to three different values and under the self-weight of each segment. This is the case of bending of a simply supported beam under the self-weight. For the 9 considered cases, the error between the experimentally measured value and the theoretical prediction is in general, as you can see here, of the order of 1-2%. And this is quite accurate because we have made many simplifying assumptions in the theoretical modeling, the most important of which are certainly having neglected the friction between the contact surfaces, and even more so between the cable and the shafts. This is the case of 4-point bending. Here and here the beam is supported, and then we have applied these forces. The self-weight is not considered here because the beam is resting or is in a horizontal plane. And in this case, for the values of the forces that we have indicated in this couple of slides before, we obtain errors which are again of the order of 1-2%, despite the very strong simplified hypothesis. We have also considered the combined action of self-weight and to a tandem and of a tandem force. Since the system is highly nonlinear, of course such effect cannot be superimposed. If P denotes the value of each force forming the tandem, this figure represents the value of the maximum sag Vmax as a function of the force P. The blue line represents the theoretical prediction, and the red dots are the experimentally measured points. We have added a third graph, represented in green, which is referred to as the first order approximation. And this graph corresponds to the case in which we neglect the increase of tensile force in the cable due to its elongation, which is equivalent to assume that the tensile force in the cable remains equal to the initial pre-stress N0, irrespective of the elongation, second order elongation of the cable. The two series of graphs corresponds to two different values of N0, 51.1 Newton and 33.2 newtons. It should be observed that the higher is the tensile force in the cable, the more accurate is the first order approximation, so that the green and blue curve are closer. This is because the increase of tensile force becomes percentually smaller with respect to an initial pre-stress. In this second graph, we show again the maximum sag Vmax as a function now of the initial pre-stress N0 for a given applied load, each one of these two forces equal to 0.5 Newton. Of course, you find out that the higher is N0, initial pre-stress, the smaller is the sag. In addition, you find that the difference between the first order approximation and the theoretical prediction becomes small as the initial pre-stress is increased. We are now ready to drive the conclusions. We've shown that flexural tensegrity provides a possible way to manufacture beam-like structure which is governed by Taylor-constitutive relation. And the key point is pre-stressing the segments in unilateral contact with tendons. The construction is very simple because the joints are made with machine components without minute parts that may be potentially subjected to breakage. Robustness can be obtained by using more than one cable. Of course, the tailored design of hinge-based and self-aligning foldable structures with a tunable response has many potential applications which range from biomedical structure for prosthetics to reconfigurable surgical tools, low inertia cable actuated compliant beams for robotics, structures with morphing capability and elastic tailoring for aerospace use, structural elements used alone as a beam or as an arch or assembled in the form of spatial grids for transforming architecture. What I have tried to explain in this talk has been recently published in the Proceeding of the Royal Society of London. Here is the reference, and you can find more details here. This work develops an embryonial idea which was first presented in this other paper together with Valentina Beatini, published in Engineering Structures. Thank you very much for your kind attention.